This is the Electric Fields Homework Booklet, question 33. You are asked to describe how a beam of fast-moving electrons is produced in a cathode ray tube of an oscilloscope. So first of all, thinking about how the electrons are produced. So the cathode will normally have a current flowing through it. You can have an indirectly heated cathode, but very often it is just a filament that the current flows through. This causes the cathode to be heated. Next, you can identify the process thermionic emission, which causes the electrons to then leave the cathode. It provides the energy required to overcome the work function. Next, consider that you are asked to describe how it is a fast beam of moving electrons. So we can consider that the electrons are accelerated, having left the cathode, towards an anode by an electric field, or a high potential difference applied between the cathode and the anode. Next, we see a diagram of a cathode ray tube. And a number of dimensions are given within the diagram, and just carefully reading the text helps you to confirm and take in that information. So an electron beam passes between two horizontal plates and goes on to strike a fluorescent screen at the end of the tube. The plates are 0.04 meters long and are separated by a gap of 0.015 meters. A potential difference of 270 volts is maintained between these plates. This value is not given within the diagram. An individual electron takes 1.5 times 10 to the minus 9 seconds to pass between the plates. And the distance between the right-hand edge of the plates and the screen is 0.20 meters. You are asked to show that the vertical acceleration of an electron as it passes between the plates is approximately 3.2 times 10 to the 15 meters per second squared. Here you're bringing together three different equations to solve the problem. So acceleration of the electron would be given by force divided by mass. Here we have the electrostatic force, which is the charge on the electron multiplied by the electric field strength. And finally, for parallel plates, the electric field strength is given by the potential difference divided by their separation. Putting all of that together leads to an answer of 3.16 times 10 to the 15 meters per second squared. Note how I have given my answer to one more significant figures than that suggested in the question. This is good practice and is very often required in mark schemes. Next, you are asked to show that the vertical distance travelled by an electron as it passes between the horizontal plates is approximately 3.6 millimeters. Here you can start to think about the fact that the horizontal and the vertical motion are independent. So for this question, we only need to consider vertical motion. We want to know the vertical distance travelled, so that is our question. The initial vertical velocity will be 0 because the electrons were initially moving horizontally. We don't know the final vertical velocity. We have just found the acceleration in the previous part of the question, and we were also previously given the time to pass through the plates. So here, using an equation avoiding v gives us s equals ut plus a half at squared, and we lose this term since the initial velocity was 0. So simply a half times the acceleration times the time squared, leading us to an answer of 3.56 times 10 to the minus 3 metres. Again, quoting one more significant figure. Next, you are asked to find the vertical component of the velocity achieved by an electron in the beam by the time it reaches the end of the plates. This is exactly the same situation as the previous part of the question, so the list remains the same, and we want the final vertical velocity. So v equals u plus at simplifies to the acceleration times the time and gives us a value of 4.74 times 10 to the 6 meters per second. Finally, you are asked to calculate the vertical displacement of the electron beam from the centre of the screen, giving your answer in meters. Just take a look back at the diagram to consider the situation here, and you will see that this vertical distance y is made up of two parts. There was the vertical displacement within the plates, and then a further displacement whilst the electron passed from the plates to the screen. Within the plates, we had a constant vertical acceleration, whereas once the electron leaves the plates, there is no longer a force acting on it, and you'll notice that this is drawn as a straight line, which is correct. Strictly, we should really be seeing a parabola inside the plates, but we have a straight line here, and so this is constant velocity in the vertical direction for the second part of this journey. So going back to the solution, we can consider the journey of the electron from the end of the plates to the screen. We know that it experiences constant speed and that the horizontal speed has never changed during this problem. So we now need to know how long the electron will be travelling between those 2 points. Now, we know the horizontal speed is constant, so the journey time will relate directly to the distance. Looking back at the diagram, we had 0.04 metres within the plates, and we had 0.2 metres between the plates and the screen. So that is 5 times greater distance for the electron to travel from the end of the plates to the screen than when it was within. That means it's going to take 5 times as long to travel that distance. Having worked out the time of travel, we can work out the vertical distance moved in that time. We have already, in a previous part of the question, worked out the vertical velocity at the end of the plates. This was 4.74 times 10 to the 6 meters per second. So we multiply that vertical velocity by the time of flight to give the distance travelled between the plates and the screen. Finally, to get the total vertical distance, we need to add on the smaller vertical distance that the electron moved whilst travelling between the metal plates. Combining these leads us to an answer of 3.9 times 10 to the minus 2 metres.